So we know that Ka into Kb is equal to ionic product of water Kw. This can be extended to make a generalization. The equilibrium constant for a net reaction obtained after adding two or more reactions, it will be equal to the product of the equilibrium constants for individual reactions. That is, K net will be equal to K1 into K2 into etc. Similarly, in the case of a conjugate acid-base pair, Ka into Kb will be equal to Kw. Next, we shall discuss about di and polybasic acids. HCl is a monobasic acid. Sulfuric acid H2SO4 is a dibasic acid. H3PO4 is a tribasic acid. Now consider NaOH. It is a monoacidic base. Now consider calcium hydroxide CaOH twice. It is a diacidic base. Now consider dibasic acid H2X. This acid will dissociate in two steps. H2X dissociates to give H plus and HX minus. HX minus then dissociates to give H plus and X2 minus. So the dissociation takes place in two steps. For the first step, dissociation constant Ka1 can be written as equal to H plus and concentration into Hx minus concentration divided by H2X concentration. Similarly, for the second step, the dissociation constant Ka2 can be written as equal to H plus ion concentration into X2 minus ion concentration divided by Hx minus concentration. Next, we shall discuss about the factors affecting acid strength. Consider the following acids HF, HCl, HBr and HI. The acid strength increases as we move from HF to HI, which means HI is the strongest acid. What is the reason? See, if we consider HF, HCl, HBr and HI, there is a change in the halogen atom, fluorine, chlorine, bromine, iodine. We know that size of the halogen atom increases as we move from fluorine to iodine. So as the size of the halogen atom increases, the acid strength also increases. Next, consider methane, ammonia, water and HF. Acid strength increases in the order methane less than, ammonia less than, water less than HF. Why is it so? For that, consider carbon, nitrogen, oxygen, fluorine. We know that electronegativity increases as we move from carbon to fluorine. Fluorine is most electronegative. So as the electronegativity increases, acid strength increases. Next, we shall discuss common ion effect in the ionization of acids and bases. For example, consider the dissociation of acetic acid. Consider the dissociation equilibrium. Acetic acid dissociates to give H plus and acetate ions. Acetic acid is represented as HAC. Acetate ions are represented as AC minus. So dissociation constant Ka can be written as equal to H plus ion concentration into acetate ion concentration divided by acetic acid concentration. So now we have an equilibrium. To this equilibrium, if we add sodium acetate, it will supply acetate ions. Acetate ions are already present in this acid equilibrium. Now when we add sodium acetate, it will supply acetate ions. This ion is present in the acid equilibrium. So addition of acetate ions will increase the concentration of acetate ions. So the system will try to decrease the concentration of acetate ions by favoring the backward reaction. As a result of which, there will be a suppression in the dissociation of acetic acid. So this effect is known as common ion effect. So how can we define common ion effect? It can be defined as a shift in equilibrium on adding a substance that provides more of an ionic species already present in the dissociation equilibrium. So this is based on Le Chatelier's principle. To the acid equilibrium, if we add a substance which supplies a common ion, then it will cause a suppression in the dissociation of the acid. So this suppression in the dissociation of the acid by the addition of a substance that provides a common ion is known as common ion effect. Next, we shall consider hydrolysis of salts. Here we have to consider three different types of salts. Salts of weak acid and strong base, example sodium acetate, salts of strong acid and weak base, example ammonium chloride, and salts of weak acid and weak base, example ammonium acetate. First consider sodium acetate. Sodium acetate dissociates into acetate ions and sodium ions. Acetate ion thus formed will react with water to give acetic acid and OH minus ions. Acetic acid formed is a weak acid, so it will remain mainly unionized in solution. This results in an increase of OH minus ion concentration. Therefore, the solution will become alkaline and the pH of the solution will be more than 7. Now consider ammonium chloride. It dissociates into NH4 plus and Cl minus. Ammonium ions thus formed will undergo hydrolysis with water. It will react with water to give ammonium hydroxide and H plus ions. We know that ammonium hydroxide is a weak base, so it will remain unionized. So this will result in an increase in the concentration of H plus ions. Therefore, the solution becomes acidic, or the pH of ammonium chloride solution will be less than 7 since it is acidic. Now consider ammonium acetate. It will react with water to give acetic acid and ammonium hydroxide. Acetic acid and ammonium hydroxide also remain into partially dissociated form. From acetic acid we get acetate ions and H plus. Ammonium hydroxide dissociates into NH4 plus and OH minus, and water dissociates into H plus and OH minus. Now pH of solution here in this case is given as equal to 7 plus half of pKb, pKa minus pKb. Next we shall discuss about buffer solutions. Solutions which can resist the change in pH on dilution or with the addition of small amounts of acid or alkali are called buffer solutions. We have two different buffer solutions, acidic buffer and basic buffer. For example, a mixture of acetic acid and sodium acetate is acidic buffer and it has pH around 4.75. A mixture of ammonium chloride and ammonium hydroxide is basic buffer and it has pH around 9.25. An acidic buffer can therefore be prepared by mixing weak acid and its salt, whereas a basic buffer can be prepared by mixing weak base and its salt. Next we shall consider solubility equilibria of sparingly soluble salts. Solubility depends on two factors: lattice enthalpy of the salt and solvation enthalpy of the ions in solution. So for a salt to dissolve in a solvent, the strong force of attraction between the ions, that is lattice enthalpy, must be overcome by the ion-solvent interactions. Solvation enthalpy is always negative because energy is released. Consider a non-polar solvent. A non-polar solvent has smaller solvation enthalpy. So it is not sufficient to overcome the lattice enthalpy of the salt. Therefore, salt does not dissolve in non-polar solvent. Next we shall discuss solubility product constant Ksp. For example, consider barium sulfate. Consider a saturated solution of barium sulfate. Such an equilibrium exists, that is barium sulfate reversibly giving barium ions and sulfate ions. The equilibrium constant can be written as K is equal to barium ion concentration into sulfate ion concentration divided by concentration of barium sulfate. But for pure solid substances we know that the concentration remains constant. Therefore we can write solubility product constant Ksp is equal to barium ion concentration into sulfate ion concentration. And for barium sulfate, Ksp is given as equal to 1.1 into 10 raised to minus 10. But Ksp is equal to solubility S square. So we have 1.1 into 10 raised to minus 10 is equal to S square, or S equal to, that is solubility is equal to 1.05 into 10 raised to minus 5. Now consider common ion effect on the solubility of ionic salts. For example, consider sodium chloride. Consider a saturated solution of sodium chloride. If hydrogen chloride gas is passed through saturated solution of sodium chloride, then sodium chloride will get precipitated. It is due to increased concentration of chloride ion available from the dissociation of HCl. So sodium chloride thus obtained will be of very high purity, and we can get rid of impurities like sodium and magnesium sulfates. Common ion effect is used for almost complete precipitation of a particular ion, as it's sparingly soluble salt with very low value of solubility product. It is for gravimetric estimation. Thus we can precipitate silver ion as silver chloride, ferric ion as its hydroxide, and barium ion as barium sulfate for quantitative estimations. Now consider the solubility of salts of weak acids like phosphates. The solubility increases at lower pH. This is because at lower pH, the concentration of the anion decreases due to its protonation. So this in turn will increase the solubility of the salt so that Ksp will be equal to Qsp.